Hello, math student. In a previous video, we looked at the direct comparison tests. These are closely related to the limit comparison tests, which we're going to take a look at in this video. I like the limit comparison test actually because I think it's easier to use than the standard comparison tests, although there are some cases where you have to be a little careful with how you think about things. So the limit comparison test says the following. Suppose we have two infinite series of, again, positive terms. Again, this test, like the others we've looked at, does not work if we have some negative, some positive terms. So suppose we have an infinite series of positive terms, and we take a look at the ratio of terms, ak to bk, and take that limit as k goes to infinity. Suppose we get some answer L for that limit, and L turns out to be a finite and strictly positive number. If all that happens, then these two series, summation AK, summation BK, either both converge or both diverge. So in other words, if you know what one of them does, then you know what the other does. Now, in this test, I can't overstress the importance that the L that we get, this limit up here, must be positive, not zero, and finite. In the case when L equals 0, L equals infinity, you have to be very careful in drawing conclusions. You might get some information and you might not. We'll take a look at those cases later in the video. So when we use the comparison test in this discussion, we're usually going to take AK, summation AK, to be a series whose convergence, divergence we wish to determine, and summation BK to be a series whose convergence or divergence behavior we know. Okay. So the way that this comparison test works, then you get a series summation AK, you're asked does it converge or diverge, and then you have to decide on a series BK to compare it to, and again, we'll take a look at some techniques for deciding what that comparison series should be. But the second series has to be chosen kind of carefully for two reasons. One, you certainly want to make sure that when you go to compute this limit, it is a limit that is easy to compute and is finite and non-zero. And of course, you want a series for which you know the answer, does it converge or diverge? So all these come into our considerations. So let's start with example 1 here. Determine whether the infinite series summation r equals 0 to infinity, 5 times 3 to the r over 9 times 2 to the r plus 4 to the r converges or diverges. So we're going to use the comparison tests. Again, we're going to take the series we are wondering about to be the AK series, or the AR series in this case. So in this discussion, AR is just going to be the general term of the series, 5 times 3 to the r over 9 times 2 to the r plus 4 to the r. And we're going to then find an appropriate infinite series summation BK, whose behavior we know, and to compare it with. Now, as we did with the direct comparison test, we can usually find the other series to work with by doing a little scratch work on the side. So again, we often take a look at numerators and denominators, and in this case, we reason as follows, that if r is very large, then the 4 to the r term in the denominator is going to be bigger than 9 times 2 to the r. You raise 4 to a large power, you're going to get much, much, much bigger than 2 to a large power. And so based on that, we kind of expect, again, looking at dominant terms in the numerator and denominator, that this series should look a lot like, at least when r is large, the term should look a lot like 5 times 3 to the r over 4 to the r, or as this works out to be 5 times just 3/4 to the r. So we're going to see in this case the 5 isn't that important, so we're going to take for our b sub r the term 3/4 to the r, which is the main term that came out here in this comparison. So we're going to compare our series, the AK series up here, to the series summation 0 to infinity, 3/4 to the r. So the limit comparison test says that we do this by taking the series we're curious about, the a sub r series. There's its term. and divide by the terms of the other series BR, which was 3/4 to the R. And of course, this series, summation 3/4 to the R, is a convergent geometric series. The ratio is 3/4 less than 1. Now, let's evaluate this limit. So we do a little algebra, invert and multiply to divide the fractions, and then do the exponential calculations in top. We get 5 times 12 to the R in the numerator, because 3 to the R times 4 to the R is equal to 3 times 4 to the R, or 12 to the R, and then similar work in the denominator. Now, as we did back in Calc 1, when we want to evaluate quotient expressions like this, often it's a good idea to divide top and bottom by the largest expression in the numerator and denominator. In this case, that's 12 to the R, which is much bigger than 6 to the R. So if I divide top and bottom by 12 to the R, as we did here, do the algebra, we find this comes out to be 5 over 9 times 1/2, that's 6 over 12 to the R, plus 1, and this all turns out to be just 5. So this is our L in the limit comparison tests, and since L is a finite and non-zero number, both of those are important, we know these two series have to behave the same. And of course, as we mentioned, we know this one converges. This is a convergent geometric series, ratio of 3/4. And that means this series must also converge. Again, this test doesn't tell us anything about the sums. They do not necessarily converge to the same sum, and in fact, they rarely will. Let's look at another example. So if you watched the video on the direct comparison test, you saw this example in that video. Let's see how the limit comparison test can be used to kind of make the work a little easier. So we start with the same analysis we do with the direct comparison test, realizing that when J is large, that in the bottom, the dominant term is the J. It's bigger than all the other stuff down here. And by large, I mean much, much bigger than 1492. So the 1492 is negligible, as well as the square and cube roots of J. The top, of course, there's just one term, so that is dominant in the top, 4th root of J. And so we expect this series to behave like the 4th root of J over J, or 1 over J to the 3/4. So, as usual, we're going to call this our AK series, and the BK series is the one formed by these terms 1 over J to the 3/4. And so we're going to be comparing the series we're given with this series using the limit comparison test. And of course, as we know, we already know this comparison series is a divergent P series. The P is equal to 3/4 less than 1. So we again look at the ratio AJ over BJ. So here's the AJ, the terms of the series we're curious about. Here's the BJ, the terms of the series we are comparing to. And again, some algebra, invert and multiply. And then do the multiplications in top. And we come up with this expression as J goes to infinity. And again, as we did in Calc 1, we say, well, the J is the biggest term at the top, J is the biggest term at the bottom. So we divide top and bottom by J. And when we do that, little algebra gives us this expression down here with 1 at the top. And as J goes to infinity, all these terms go to 0 to give us a limit of 1. So in this case, the L equals 1. And again, finite, non-zero. And so we can conclude that the two series we compared behave the same. And since this one diverges, that implies that one also diverges. Now, the way the limit comparison tests work, it's really based on the direct comparison tests. So let's just take a moment to kind of see why this is plausible. So if we have a non-zero finite limit for this ratio, there's L. So it's finite, less infinity, and positive. Okay, now this means that when k gets big, this number L is this ratio, rather, AK over BK is getting close to L. So in particular, it's eventually going to get bigger than L over 2 and less than 2L. So if you look at the number line, there's L over 2, there's L, and out here might be 2L. And eventually all the AKs over BKs, if they're getting close to L, are looking something like that. Okay. Now, what that means is that when k is large, that then the AKs over BKs, they're going to be close to L, so they're going to be somewhere between L over 2 and 2L. Again, they have to get close to L, and getting close to L means getting further and further from other numbers. And so if we are convinced this inequality is true, then we can go through and multiply both sides, or all three sides, by BK, and we have L over 2 BK less than AK less than 2L BK. And this is starting to look a lot like those comparison tests, the direct comparison tests we saw in another video. So this left inequality here tells us the AK's bigger than the BK's, essentially. And so we know that if that lower sum diverges, the BK's diverge, then so does the AK, because its sum is going to be bigger. Marginal factor of L over 2. And conversely, if you pay attention to the other inequality over here, here it shows the AK's are in essence less than or equal to the BK's. So that means if the BK's converge, then so do the AK's. So that shows how we can infer that the two series behave the same. Now, finally, we talked about the care needed if you have a limit of 0 or infinity. And this can arise sometimes. Often it arises from maybe a non-optimal choice of the series BK to converge to. In these cases, it might be possible to get some information, but you got to be kind of careful. So let's suppose then we know about the BK series, want to find out about the AK series, and let's see how we can use this kind of information. Okay, case 1, let's suppose that this limit AK BK turns out to be 0. Now, if k is large, that means AK over BK is small. It's a small fraction. So if you're converging to 0, it means you're getting small. So if this is a small fraction, that means the numerator is less than the denominator, so the AKs are less than or equal to the BKs. Now, what information can you get out of this? Well, this tells us that if the BKs converge, then we're going to, and of course, because they're bigger than the AKs, then the AKs will converge. Notice, though, if all you know is that the BKs diverge, that is, this sum's infinite, you can't say anything about the AK sum. So this is kind of half a test in this case. If the limit is 0 and the unknown term is in top there, then if the BKs converge, then the AKs converge. You can get other information if that limit turns out to be infinity. So suppose the limit as k goes to infinity of AK over BK turns out to be infinity, as we see here. And that means if k is large, that AK over BK is big. It's a huge fraction. And so that means the numerator is bigger than the denominator. And so now we can say that if that lower term, if the summation BK diverges, and the AKs are bigger, then the AK also diverges. On the other hand, if the BKs converge, the AKs are bigger. We don't know if bigger means infinite or just something bigger and finite. So no information that way. So bottom line, these this case where the limit L is 0 or infinity, you might get information, but you have to think it through every time. Don't try to rely on memory. Think it through. Ask, does this logic make sense? If I have something that converges and I have something smaller, does it make sure the sum of the smaller stuff converges? Yes. But try to avoid making, of course, the wrong implication. So what are the takeaways here? So if we want to determine the convergence and divergence of a series summation A sub k in a limit comparison test, it's often a good idea to consider the largest terms in the numerator and denominator. And those kind of you can use those to estimate what you think the BK series should be. The most commonly used series are the P series, summation k minus 1 to infinity 1 over k to the p. As we saw when we studied the integral test, those series converge if p is less than or equal to 1 and diverge if p is bigger than 0. You have to know these series and be comfortable working with them to do well with this subject. And finally, get in the habit of thinking through your conclusions to make sure they make sense. Don't let yourself work on automatic pilot and stop thinking about things. This is especially important in the cases where the limit of the ratio ak to bk is either 0 or infinity. Think very carefully, can information of the summation of bk give you information about the summation of the ak? Okay, so do some practice with this, and I think you'll find this is a slightly easier test to use than the direct comparison test, so this is one I think it's really a good idea to focus on. Thanks very much. Bye.